Hello again, statisticians. Here back for the first lesson of sampling distributions. We just finished normal distribution and just kind of introducing the idea of the bell curve. Normal distributions are great if something appears in the real world in a normally distributed fashion that's convenient for us, as ACT scores, SAT scores, IQ, and the like do. However, it's more common that a distribution in the real world will not be normal. In other words, will not be bell-shaped. And so we need to have a way to remedy that, and to try to get other distributions to be bell-shaped, and that's where sampling distributions come in. So sampling distributions are an extremely important gateway for us, in that they allow us to, through a process, get non-normal distributions to be normal, so that we can then perform inference procedures with them, like the t-tests and the proportion tests that are going to come after this. So let's jump into what a sampling distribution is here. What you need to know for this, first of all, is the difference between a statistic and a parameter. Okay, a statistic for us here would be an X bar. A parameter would be a mu. So this here is a sample mean, and I'll have these organized here later as well. And this is a population mean. So if we were talking about heights of students at Minnetonka, X bar might be the average height of 30 students, okay? Whereas mu is the average height of all 3,200 students. Okay, so you see the lowercase n for the sample, the uppercase n for the population size there. The other statistic we'll be working with is a p hat, which is a sample percentage or proportion. Okay, and the alternate to that is p, which is a population proportion. Okay, in much the same way, the sample proportion would be the percent of a sample of 30 students who like having an open hour, where the population proportion would be the percent of all students who like having an open hour. So again, X bar goes to mu, and P hat goes to P in terms of a sample statistic and a population parameter. So we need to look at defining and creating a sampling distribution. Need to look at what unbiased estimators are, and then what high and low bias, high low variability is. So we'll jump to all those. So again, parameter, sorry, it got cut off here, is a value that describes a population. Okay, and a statistic, which also got cut off, is a value that describes a sample. Sorry about that. So a statistic is a value that describes a sample. Okay, so they each have their own purpose here. We tend to work more with statistics in that's what we find from our sample data. And questions would give us parameters because they would have information about populations, which we won't collect much on our own. Sampling distribution. A sampling distribution, this is a relatively difficult definition to kind of digest here, but of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In other words, we've got a bucket of 3,200 students at Minnetonka High School, and we're going to pull out 30 at a time. So what we do then is, let's say we're looking at heights, and heights may be centered around 68 inches in our building. And so what we do is we essentially take out one sample of 30 and we find their X bar. Okay, and their X bar happens to be 68 inches. Okay, so that's our first sample. Then we put those 30 back in, mix it up, and take out another 30. It might overlap with the first 30 by one or two students, or it might not. And that X bar ends up being 67 inches. And then we put those back in, and we mix it up, and we pick out another 30 and get their X bar. And their X bar is also 68 inches. And then we put those back in, we mix it up, and we get another sample of 30, and we get their X bar, which happens to be 69 inches. Okay, and we continue to do this over and over and over again. And by we, I mean typically a computer will do this because it's a very time-consuming and kind of rigorous process to get all possible samples since there's millions of them. But we keep doing this and we simulate it and we end up getting a sampling distribution. So what we're doing is we're just getting a bunch of X bars, okay? And then we're graphing the X bars like they're their own histogram of sorts, okay? And of course, when you see this histogram, then you start to see the shape and so on. And what happens is this helps us in situations where height at our high school might be close to normal already, although with the 9th and 10th graders, there may be some who are just shorter, still growing, so it might be a little skewed to the left. But sampling distributions could take that skew and kind of fix it, if you will, and get this normal sampling distribution. Now, keep in mind, a normal distribution, or the original distribution of heights, is individuals. Okay, so there might be 500 students who are 5'7" and 700 students who are 5'8", and so on. So that's individuals. Now, sampling distributions never look at individuals, they look at individual samples. So each one of these is 30 people. And again, it might be 30 unique people or it might be some overlap. It's all possible samples. So that would be you with any other collection of 29 other people in our school. So what we do, and again, I don't know what happened here with this formatting, but we take a large number of samples from a population, okay? And again, that's typically millions, which we use a computer for. We get the p hat or the x bar, so it might be instead of average height of those 30, we might be taking what proportion of those 30 like massed, or what proportion of those 30 are in extracurricular activities or something like that. And then we graph each one of those p hats or x bars, okay? And then eventually we'll use that graph to solve probability questions of some sort, okay? And we'll see that moving forward. So the graph itself, if we switch over to percentages, if it's what percent of students like massed, and let's say we're around 70%, and this might be a little wider range, so we're going to split it up a little more, but we'll still give a bin for each one. So there might be a p hat here, and a p hat at 71, another p hat at 70, a p hat at 69%, p hat at 67%, p hat at 73%, another one at 71%, another one at 70%, and so on. And again, there'd be millions of these p hats, and we would ultimately find ourselves in a normal distribution. Okay, so this is an example on the p hat side where it's all that really changes is the scale. Instead of 68 inches in height, it's 68%. And so instead of X bars, it's P hats. And ultimately, we're just creating a histogram and then getting to that normal curve. Now, when we look at this, we want to make sure that we have an unbiased estimate. In other words, if we're working with heights, we want the center of our sampling distribution to truly be at the overall average of our school. And the way we would define that is the mean of the X bars equals mu. Okay, so again, what we mean by that is the sampling distribution should be centered at 68 inches if the population average height in our building is 68 inches. Okay, if the percent of students who like massed is 70% in our building, and we knew that by surveying everyone, then the distribution of percentages should be centered at 70. So that would be that the mu of the p hats, meaning the average of all these p hats, equals the population average. Now again, these are population values here, okay? And these here are averages of your samples. Okay, so this would be this right here would read as the average of all of our X bars equals the overall average. Here, the average of all of our P hats would equal our overall proportion. And that's called being unbiased. And that will just sort itself out if you take random samples. Okay, so if our samples of 30 are truly collected randomly, then this will be true for each one of these, and that's where the idea of being unbiased comes from. Now, decreasing variability, okay, decreasing variability is the idea that our graphs here aren't so wide. Okay, in other words, if we were doing heights and we only took 2 people at a time, okay, there might be some average heights of 2 people that are all the way up by 72 inches or something like that. Okay, and so if we have a really wide graph, then that's not terribly precise. And that happens if we have too small of a sample size. Okay, so we might end up getting a couple X bars here and a couple more here. Okay, so we're still centered in the right spot, but then we got a bunch over here still because we just didn't take big enough samples. Okay, so the variability is all about having big enough samples. Okay, now these two ideas right here, being random for the sake of being unbiased, okay, and having a big enough sample for the sake of having less spread, are two things that are very important in their own right. So the random sample kind of speaks for itself. You can't cheat and just pick tall people or short people if you're trying to find the height of students in our school. The big enough samples piece, if you have too small of a sample, you might not achieve your ultimate goal with the sampling distribution, which is to get to the idea of normal. Okay, so if you only select 2, if something's skewed, like if we're talking incomes in our district, and we only select 2 families at a time, we aren't going to fix that skew. Okay, it might be a little less skewed with samples of 2 instead of 1. Okay, because that $5 million family will be, with a $500,000 family, and that waters down the average a little bit, but we're still going to be skewed. And so what we do is we kind of set a threshold, and the threshold here is actually that if we're talking means, each sample, as I've referred to already, should be 30 or more. If we're talking proportions, the rule is actually that the sample size times p, which is the population proportion, and sample size times 1 minus p should each be 10 or more. And that's kind of our threshold that we use, that's been proven over time, to make sure that we achieve this idea of a normal sampling distribution, which is our goal with all of this. Okay, so we want it to be random so it's fair, but the sample size we need to have be big enough, because the whole reason we're completing these sampling distributions is to achieve normality in the sampling distribution. Now, the proportion one quickly here, this is kind of like looking at the number of successes. So if we had a 70% chance of success and we had 100 people, we'd have 70 successes on average. And then this is the number of fails. Okay, so this is, we've got 30% are fails, and out of 100 people, then we should have 30 fails. And fail could be saying no to, do you like The Bachelor? It could be saying that it could be that you don't like Mast or whatever it happens to be. So those are the two biggies. So bias comes with the sampling, the random sampling. Variability comes with the sample size. So if we look at this example here with political polling. So in a political polling situation, I'm going to change these actually to E's here for standard error, because we'll base off the sample size. So in this situation, we've got a sample size of 100. The P equals 0.6, which means 60% of people support a candidate or whatever it may be. And when we look at this, then the standard error is close to the margin of error, and we'll get into what the difference is later on. But what we're looking at here is really saying that if our sample is 100, then we have a P of 60%, but we are kind of give or taking 5% there. Okay, so that's the variability piece. It's, again, not quite margin of error, but kind of like that we're saying it's 60%, give or take 5%. Okay, so this, we're kind of certain that it's somewhere between 55 and 65%. Now, similarly, if we take an N of 2,500 and we still use 60%, now our standard error is 1%. So now we're saying this candidate is going to receive somewhere between 59 and 61% of the vote to be within one standard error. So you can just see the kind of accuracy that comes with this, in the sense that there's a smaller window of potential values. So it's like we zoomed in a little bit and made sure to be a little more accurate. And that again comes with the bigger sample size. So if a company is doing some political polling in advance of an election, they want to be cognizant of how many people they're going to ask, because how many people they ask is going to determine ultimately what their margin of error ends up being. So when they put that poll up on a TV screen, they don't want it to read 8% margin of error, because that means a candidate could get 50%, give or take 8%, which is a width of 16%, which is just would be wildly inaccurate in terms of being precise, at least to report. But if they ask a bunch more people, thousands of people, then they can start to report really small margins of error and saying that this candidate is supported at this rate, give or take 1 or 2 or maybe 3%. You tend to see between 3 and 4% as a margin of error on TV. So quickly here, the things to think about: the difference between bias and variability. Again, bias is about being honest with that random sample, and variability is about the spread, which is decreased as the sample size increases. So again, as n goes up, variability goes down, would be the rule there. Bias, we said, is controlled by the randomness. Variability is controlled by the size of the n. And the primary goal of a sampling distribution is really to try and fight to that normal sampling distribution in a fair fashion. Okay, so end with a quick little activity here. When you look at the idea of bias and variability on a bullseye, okay, again, what we're shooting for is low bias, low variability. And that would be like a bunch of darts hitting very close and tight into the bullseye. Again, low bias is because we had an SRS, and low variability is because we had a big N. Okay. Now, if we had low bias but high variability, that means we'd be centered around the bullseye, but the values would be the darts would be spread out. Okay. And this again would mean that we had an SRS, but we had a small sample size. Okay. So that's the idea of having being centered at 70%, but having that standard error be 5% instead of 1% in that case. Now, if we have high bias and low variability, that means we cheated. We went to the basketball practice to get heights, but we took a big enough N. We took 20 basketball players at a time, but we did not take an SRS. And then finally, the worst would be high bias, high variability. And in that situation, we are all over the place and not even close to the bullseye. So in that situation, we didn't take an SRS. We went to basketball practice and we asked 2 players at a time. Okay, so that's the distinction there at the end. Again, that's what we want to achieve, is low bias, low variability. A random sample for each one of the samples in the sampling distribution, and a big enough sample size to ensure that we're pretty precise. Thank you for listening and watching. If you have any questions, as always, please ask.